We're good.
It's okay.
It's okay.
Oh,
Let me just.
mm, is it good?
Yep, we should.
Oh,
be good
it's
now.
good, right?
Yep.
Oh, okay. Thank you.
And now we just need to go back to the.
Hmm? Okay. Okay. Yeah. Let's get started. Yeah. So first of all, thank you for the invitation. So my name is Jiawei Zhang, and I'm a new assistant professor in computer sciences. Today, I'm very happy to share our recent research. Okay, so from the textbook result, we know that we are interested in generic optimization problems, minimizing objective function effects. We usually assume f is lower bounded, and usually we assume f is Lipschitz smooth, has Lipschitz continuous gradients, or equivalently speaking, if f is twice continuous differentiable, we can. I mean, this is equivalent to say that the special norm or largest singular value for the Hessian matrix is upper bounded by L for every x. So for solving this optimization problems, the most simple algorithms are gradient descent GD and stochastic gradient descent SGD. So GD is just this xt plus 1 equals xt minus this step size times gradient. And for SGD, we replace this gradient by an unbiased estimator for the gradient. Though like this GD and SGD, they are very simple, but they're very powerful, especially for large-scale optimization problems. Most practical algorithms for large-scale very large-scale optimization problems are based on GD, SGD. Computation steps are very simple. We just need first order derivatives, and especially when you have you have data-driven optimization problems or like machine learning training, SGD is more preferred as to compute the batch gradient or just a gradient at one sample. Requires much less computation capacity. Okay, so let's look at the basic convergence results for GD and SGD. We focus on nonconvex optimization problems, so we try to find epsilon stationary points for the optimization problems. For GD, okay, so for GD, we have so we usually choose constant step size 1 over L. So L is the Lipschitz smoothness constant. So if we choose constant step size, then we can have this iteration complexity over epsilon square. For SGD, if you choose the step size epsilon square over L, then we can have the sample complexity and the iteration complexity L sigma square over epsilon to the power 4. Here, the sigma square is the variance for the gradient estimation. So we can see that for the deterministic case, the gradient descent has the iteration complexity with order 1 over epsilon square, and the SGD is 1 over epsilon to the power 4. And all of these step sizes and the convergence rate depends on the Lipschitz smoothness constant L. Okay.
Display time.
Okay.
Is that it would be full screen? I think that's good. Yeah, okay. Continue.
Oh, okay, thank you. Okay, so corresponding to the previous convergence result for GD and SGD, we have natural open questions. The first two questions are, for many practical problems, we have constraints. Like for many engineering, machine learning applications, we have constraints for the optimization problems. Previously, we talked about convergence results for unconstrained problems. But if we have constraints, or furthermore, if the constraints are stochastic, I mean, what's the convergence rate? Can we still have the same convergence rate or sample and the sample capacity for both a deterministic case and a stochastic case? So for deterministic case, we try to also still have 1 over epsilon square iteration capacity, and for a stochastic case, we want to have 1 over epsilon to power 4 sample capacity. So here for constraint optimization problems, first order algorithms means we can only do gradient iterations, and we can only do projection to set. Instead of very complex sets, we can only do like projection to Bohr's box like this. So these two are these two questions will be addressed in first part of this talk. The second part will be about another question. So previously we know that the set size choice and the iteration capacity depends on the Lipschitz smooth constant. Usually we assume that we have uniform Lipschitz smoothness constant. But I mean, this kind of estimation is very loose because I just mentioned Lipschitz smoothness constant is just related to the metronome of the Hessian matrix. But Hessian matrix can be very different for a different x, especially for very large scale problems. So is it possible to choose adaptive step size using the local Lipschitz smoothness information to accelerate gradient descent? So this is the question I want to answer in the second part. We will have this outline. So for the first part, we would discuss optimal first order algorithms for solving constraint optimization problems. I will review our previous results on deterministic problems and our recent results for stochastic problems. In the second part, we will talk about a recently very popular policy optimization algorithm for large language model reasoning called GRPO. We show that GRPO is actually an adaptive gradient descent. So GRPO can have much faster convergence rates, much better empirical behavior. Okay, let's first review the deterministic case. For deterministic case, our previous work on these types of problems. We try to minimize fx subject to constraint ax equals b, x belongs to this capital X. Or another problem is minimizing fx subject to some inequality constraints, gix smaller than or equal to 0, still x belongs to this capital X. We assume that this capital X is convex and it's closed and it is simple and easy to do projection. But I just mean capital X is easy to do projection, but like combining this equality constraints or inequality constraint, the whole constraint can be very difficult to do projection. So when for the algorithm design, we can only expect to do projection to this capital X instead of the whole feasible set. Okay, so in our previous papers, we show that we design first order primal dual methods that can achieve optimal iteration complexity for this problem. Suppose we have this convexity. I mean, if the objective function f is non-convex, but the constraint set capital X is convex, and this inequality constraints are also convex. So we can, for this kind of problems, we can have optimal iteration complexity, only requiring some basic constraint qualification. Okay, but we mentioned that for large-scale problems, usually we need to use stock algorithms. We can only like get access to some batch gradients. So we are interested in the sample complexity and iteration complexity for stochastic algorithms. So for the first part, we will show the optimal sample complexity of our algorithm for stochastic constraint optimization problem. Okay, this work is done jointly by me and like a co-author Ahmet. Ahmet is now an assistant professor in UBC, and he was a former postdoc of Steve. So the first author is an undergraduate student we co-supervise. So this paper is accepted by ICML this year as a spotlight. Let's talk about details. So we are interested in the following stochastic constraint optimization problems. So you notice that we have this expectation for the objective function, and also for the constraint is also an expectation of this A zeta x minus b. Okay, so we are interested in solving this stochastic constraint optimization problem. We can assume that the set capital X is easy to do projection because here we only consider linear type of inequality constraints. So this is without loss of generality. Suppose this hx more than h is not easy to do projection. We can just add slack variables w to make the inequality constraint being equality constraint, and the inequality constraint becomes only w larger than or equal to 0. Then it's easy to do projection. So this means we can assume capital X is easy to do projection without loss of generality. So for stochastic optimization problems, usually first we need to define the stochastic oracles. It means that what kind of stochastic gradient can be obtained. So we will discuss two types of oracles. For the first type of oracle, it might be you might be more familiar with. So at each iteration, we can randomly pick some sample, IID sample from the distribution, and using this sample, we can give an unbiased estimator for the gradient, for the full gradient, and we can estimate the constraint residual in expectation. So these two estimators are unbiased. So under this kind of stochastic oracle, I mean, for unconstrained problem, we don't have this estimate for the constraint residual. So for unconstrained problem, if we have this oracle, we'll have this paper in the literature shows the lower bound is 1 over s on the power of 4. So it means that SGD already achieves the optimal sample capacity for this unconstrained problem. But the question is that for constraint optimal sample connectivity. Sometimes we can have a stronger stochastic oracle. It means that for one sample, C and zeta, we can estimate the stochastic gradient at two different points and estimate the constraint residuals at two different points. So this is a stronger oracle. Under this kind of oracle, people can use variance reduction, and it is shown in the literature that lower bound of sample complexity becomes 1 over S on the power of 3. So another natural open question is, under this oracle, can we also achieve this lower bound? Actually, the answer is yes for both questions. Let me give an example for this stochastic constraint optimization problem. Just very well known example. It's a federated learning or centralized distributed optimization. We want to minimize the finite sum Fix summation Fix. So Fi belongs to one agent, and we have a central server. We introduce the consensus constraints xi equals x0, and this xi is stored in agent I, and x0 is in the central server. So at any iteration, the agent I try to send the optimization variable xi to the central server, but the link is only valid with certain probability, maybe probability p. It means that sometimes the central server cannot receive the optimization variable xi from the agent. This means sometimes we can estimate xi minus x0, but sometimes we can only have this 0 times xi minus 0 times x0 equals 0. So this means we have this stochastic constraints. I mean, the constraint matrix is different at different time. So it's a stochastic constraint optimization problem. Also, I mean, the random variable for the constraint is just the connection status. I mean, whether the connection is valid. For a fixed, I mean, at two different iterations, the connection status might be different. So it means that it's hard to compute xi minus x0 for different xi, different x0, because at any time we might have different connection status. I mean, this time we can compute xi minus x0, but next time maybe you cannot. So this means we can only have the first type of stochastic oracle. For any random variable, we can only compute the unbiased estimator of the constraint residual and the objective function at one point. Okay, so here are some papers in the literature. I will not go to the details, but just in summary, this paper is for stochastic optimization, stochastic constraint, they cannot achieve the optimal sample capacity. Also, these algorithms, most of them are based on penalty method. So for penalty method in practice, usually you need to use a very large penalty parameter. There can be some numerical issues if we want to have very accurate solution. Also, many algorithms, they are double loop or even triple loop. It means that it is not like just a single loop iterative method. I mean, you need to iteratively solve some subproblems. So in practice, these algorithms computationally can be very expensive. Okay, so here is our contribution. So we design single loop first order algorithms for solving stochastic constraint optimization problems. Our algorithm is a single loop, and we only have a constant batch size. It means that at any iteration, we only need constantly many samples. And this algorithm is a single loop algorithm. And this algorithm is based on augmented Lagrange method. So we don't need some penalty parameter to go into infinity. So this is the contribution.
By single loop, you mean that minimizing the augmented Lagrangian at each iteration, you just take one step or something?
Yeah, we just take one step. We don't need to solve any sub-problem. So here the iteration capacity is just a gradient iteration. I mean, one gradient step or one projection. That's the simple operations. Yeah. Okay. So constraint optimization problems, usually a popular approach is this augmented Lagrange approach. It works quite well for convex problems, and it has a very nice theoretical guarantee. But for non-convex problem, augmented Lagrange method can have convergence issues. So we cannot directly use the augmented Lagrange method to solve this non-convex problems. Okay, so we first review our previous works on deterministic constraint optimization problems. We want to solve the following problem: minimizing fx subject to x equals b, x belongs to this capital X. So here is the algorithm design. So we add a proximal term to the augmented Lagrange function. This proximal center is this z. So we do a gradient projected gradient descent to the function here this k, and do a dual ascent step to this y. And finally, we update the proximal center by taking average between x and the z. So this is the algorithm. Actually, we can show the algorithm can converge with 1/(epsilon)² iteration capacity for solving this deterministic constraint optimization problem. So how to understand this algorithm? So this algorithm can be understood as approximate gradient descent for the moral envelope function defined here. So we define this moral envelope function, and the update of the gradient of this moral envelope can be by Denskin theorem, it should be p is times p times z minus x bar z, and this x bar z is the solution to this proximal subproblem. But actually, we don't know this x bar z. So actually, notice that in the previous slide, sorry. So in the here we have this primal dual step for this k. This is just can be viewed as an approximation to the solution x bar z. So totally speaking, this framework is an approximate gradient descent for the moral envelope. Okay, so we can use this potential function to capture the convergence of the algorithm. So we have this term k, is minus d is the dual function. So the first step, the update of x is gradient descent to k. We can have some decrease. The second step can be viewed as gradient ascent or gradient descent to this minus d. And the third step can be viewed as gradient descent to the moral envelope. So combining these three, we can have this potential function, and we can show this potential function is decreasing, and finally show the convergence of the algorithm and the optimal iteration capacity. So previously, for the we discussed the deterministic case. A natural idea is to directly extend this algorithm to solve stochastic problem. Like the following, we use this kind of algorithm. Okay, just randomly pick some sample and do stochastic gradient projection to x and stochastic gradient descent to y. but there can be two challenges. The first challenge is about the analysis of the convergence. So notice that we have the projection for the gradient descent when we update x. We know that usually the projected gradient descent for a function, stochastic projected gradient descent for a function cannot guarantee the decrease of the function. So how to analyze this update for x? This is the first difficulty, but this is for analysis, not for algorithm design. The second difficulty is for algorithm design. So in deterministic case, we don't need to worry about the variance because we have the accurate gradients. But here we need to worry about the variance for the gradient estimator. Otherwise, I mean, the estimation can be very inaccurate. So we need to guarantee the boundedness of the variance. But the variance for the augmented Lagrange function also depends on the dual variable. So we need to make sure the dual variable is bounded. Otherwise, the variance can be unbounded. So in deterministic case, we don't have this kind of issue, but for stochastic problems, we have this issue. We need to carefully guarantee this dual variable is bounded. The first challenge, we can address this challenge by changing our potential function. So we know that from literature, I mean, projected gradient descent, stochastic gradient descent cannot guarantee the objective function value decreases, but you can guarantee the moral envelope of the function to decrease. So we can change the first term of our potential function by its moral envelope. So then we can analyze this first step for stochastic projected gradient descent. Another difficulty is how to guarantee the dual variable is bounded. Actually, if we just run the vanilla type of smooth proximal algorithms, we cannot guarantee the dual variable to be bounded. So we need to but fortunately, we can have very simple approach to address this issue. We just look at the norm of the dual variable, the multiplier. If the norm is larger than some threshold, we can just restart to set this dual variable to be 0. Okay, so this approach can guarantee the dual variable is the norm is upper bounded. Fortunately, this restarting scheme will not affect the decrease of our potential function. So we can use this approach to guarantee the dual variable is bounded and also still guarantee our potential function is decreasing. So this is the key idea of controlling the variance.
Why can't you just restart at every iteration?
No, you check the norm for the multiplier. If it is larger than some threshold, then you set it with 0. If it is,
I understand, but you say there's no drawback to doing that. So why don't you just always have weight as 0?
So sorry, you mean?
You say another way to put it is there something special about the way you choose MY?
Yeah.
Is there something special about that? Does it have to be sufficiently large?
Yeah, this NY depends on the problem itself, but actually depends on how strict the Slater condition is satisfied. Yeah. So
You need to be careful of that.
yeah. So this is the complete algorithm. So we just extend the previous algorithm for deterministic case, but just add this restarting scheme. If y larger than some threshold, we just set it to be 0. Okay. So we just keep the theoretical guarantee. So for this problem under under MAD assumptions, we can show 1 over epsilon to power 4 sample capacity, which matches the lower bound for a stochastic optimization under this first type of oracle. Next, let's talk about, just briefly talk about this variance reduction. So under Oracle 2, we can use some variance reduction technique to reduce the sample capacity. Because of time limit, I will just be quick. We will have using this variance reduction with this variance reduction. We just add this variance reduction technique to the primal variable and still use the same algorithm framework. And finally, we will have 1 over epsilon to power 3 sample capacity for solving stochastic constraint optimization problem, which matches the lower bound for the second type of oracles. Okay. So this is the first. So this is the first part. I discussed like how to design optimal first order algorithms for solving constraint optimization problems in deterministic and stochastic case. In the second part, I will try to answer the second question, like how to can we design algorithms using the local smoothness, local curvature of the objective function to accelerate algorithms. The second part is not a new algorithm I designed. I just analyzed a recently very popular algorithm for large model reasoning called GRPO, group relative policy optimization. We show that this algorithm is actually just an adaptive gradient descent. This is the work done by this Chen from MIT and my student He Qi and my collaborator from KCL. Okay. Okay, so we know recently large language model has achieved remarkable success. So this LM for reasoning is recently a very popular topic, using LM to solve mathematical problems and coding problems. So reinforcement learning and policy optimization provide powerful tools for post-training the large language model to improve the reasoning capability. Among these algorithms, this GRPO proposed by DeepSeek has achieved very good empirical success. So in this part, we will try to analyze the good behavior of GRPO. The key message is that GRPO is actually is implementing an adaptive gradient descent for the policy. So some previous approaches for this IO reasoning for language model is the supervised fine tuning, this IOHF, and the PPO, proximal policy optimization. So supervised fine tuning, the main drawback is it just memorizes the answer, but it does not capture the reasoning process very well. For this IOHF, we learn reward model from human feedback, but sometimes there can be some bias for this reward model. For this PPO, the main drawback is that we need to use a critic model. This can lead to a higher memory requirements. So we want to consider critic-free reinforcement learning algorithm. Before that, let's define the problem setting. So suppose we have a prompt or a question queue. We want to learn policies to generate the next token sequentially, and we want to maximize this accumulated reward. So usually we can use policy gradient method. We can the policy gradient is given here. So you can see to compute the policy gradient, you need to know that the value function, the Q function. But if we approximate, if we use another neural network to approximate the Q function, it will require higher memory. So we will consider critic-free kind of algorithm. Just try to estimate this Q function at any iteration. Don't do this function approximation. So in many reasoning tasks, actually, we can only have reward for the last token. I mean, for example, you can only check if the mathematical proofs are correct or the coding and the code can run. So you can only have reward for the last token, 1 if it is correct and 0 if it is incorrect. Because of this, this NDP can be regarded as one step of NDP. So later, I mean, for simplicity, we just consider one step. NDP is just the bandit setting.
So by one step, you mean you collapse the whole thing?
Yeah. Okay, so let's see this. Okay, so given this objective, so now we consider this one step, this objective function. We want to do gradient descent for this object. Actually, gradient ascent for this objective function. We just sample some answers for each questions and compute the reward, and then we can give an estimate of the stochastic. We can give an estimate of the policy gradient. This is just a stochastic policy gradient method. But the main disadvantage of this method is the variance will be very high. So to reduce the variance, people use this reinforce, so-called reinforce. This is, we try to compute some baseline model, which is the mean of the reward. And we define this advantage function to be the reward minus the mean reward. So this is very intuitive. It means that if your reward is larger than the mean, the expected reward, then you just encourage this action. Otherwise, if the reward is lower than the mean reward, you just penalize this action. So using this advantage function, using this baseline, suggesting this baseline, we can show, not we can show, I mean, in the literature, they show that this can reduce the variance. So this reinforce-based algorithms are more stable than pure like policy gradient. So what is GRPO? Actually, compared to this reinforce, GRPO just replace the advantage function by a normalization using the standard deviation for the reward. I need to highlight that this standard deviation or this variance is only for the reward, not for the policy. So this is the reward in a Bernoulli variable. So okay, so GRPO compared to reinforce is the only difference is this normalization. So the key thing we want to discuss is what's the role of this this normalization in this talk. Okay. Okay, we also make the following assumptions. Suppose for each question, we only have one correct answer, and we define this pi theta star to be the probability of choosing this correct answer. And also notice that because it's a Bernoulli variable, so the variance is just given by pi theta star times y minus pi theta star. Okay, Till now, any questions about the notation? Okay, let's move on. So, how does that compare to the policy gradients? The reinforce is just to introduce this advantage function, this baseline, to reduce the variance. But we know that's a very fundamental theory from policy gradients, that if you have infinitely many samples, then reinforce is the same as policy gradient. So here we consider infinitely many sample case. So we don't distinguish reinforce and policy gradients because the only difference for reinforce and the policy stochastic policy gradient is the introduction of this baseline, which is used to reduce the variance. But if you have infinitely many samples, then you don't need to worry about the variance reduction. So we consider the deterministic case. We have infinitely many samples. We can also compute the full gradient for the objective function. So this is a comparison of this algorithms. So now reinforced and policy gradient become the same. And the second one is GRPO. So you can see so the first algorithm, policy gradient, is just to gradient ascent for the objective function. The GRPO is just to gradient ascent, but the step size is divided by the standard deviation. So this is the only difference. It means that we just choose different step size scheme for these two algorithms. Okay, so let's go to our theory. Before that, we use this log linear parameterization for the policy. And under this log linear parameterization, we can write down the update of this reinforce and GRPO. Okay, so next we talk about the main theorem. So we have this theorem, which we can show that here the spectral norm, or maybe the largest singular value of the Hessian matrix is proportional to the variance to the variance of the reward. It's this pi theta star times y minus pi theta star. So remember that the spectral norm of the Hessian matrix is just the Lipschitz smoothness constant or also the local curvature. So this means the Lipschitz smoothness constant is proportional to the variance of the reward. Okay, remember that. So return to this algorithm. Remember that the step size is normalized by the variance. Also, this variance is just closely related to the Lipschitz smoothness constant. So this means GRPO is actually an adaptive algorithm normalizing the step size using the Lipschitz smoothness constant. And I mean, taking the inverse of the Lipschitz smoothness constant. So it means that if the Lipschitz smoothness constant is large, then we choose smaller step size. If it's small, you choose large step size. This matches our basic knowledge from textbooks. If we have Lipschitz smoothness constant, you just take the inverse of the Lipschitz smoothness constant to design the step size. Okay, so this is most important insight for this paper. So we show the Lipschitz smoothness is related to the variance. Later, we also show that the Lipschitz smoothness constant described by the variance is very stable because when we try to analyze the convergence of gradient descent, we hope that the Lipschitz smooth constant is stable in the segment connecting current iterate and the next iterate. So then we can have the descent lemma. So we also need the following. We can prove that in the neighborhood of the point theta, the Lipschitz smoothness constant is very stable. So together, I mean, combining these two results, it's very intuitive to show that. For suppose we only have one question, one prompt, then gradient, then this GRPO is just gradient descent using normalized adaptive step size, which is the inverse of the local Lipschitz smoothness constant. So we can expect that the algorithm can converge faster than using the fixed step size. In order to extend the result to many questions case, so we make the following assumptions. We assume the gradient for different questions, they are orthogonal to each other. This assumption, at least in the initialization in the early steps, can be verified by experiments. I will talk about it later. But under this assumption, it's easy to extend results for one question to many questions because the gradient, they are orthogonal to each other. This question's gradients will not affect other questions. Okay. So here is the convergence analysis for reinforce. So for reinforce, we don't have adaptive learning rate step size. So we can expect that the convergence rate is very similar to gradient descent. You can see the iteration complexity is just very similar to gradient descent using the fixed constant. Nothing surprising. But now let's look at the convergence of the GRPO. Actually, we have this one-step decrease and this key inequality and the iteration complexity. We can see that if the variance, I mean, variance pi theta star times 1 minus pi theta star is small, then the one-step decrease will be large. So also we have this iteration complexity result. We can see if during the iterations the variance is low, then the GRPO can converge much faster than the fixed step size. Okay. Okay. Thank you. Oh, sorry. This page is for GRPO. Yeah. Okay. So we show that this one-step decrease is it depends on this 1 over the variance times of the gradient non-square. So it means that if the variance is small, then we have more decrease. If the variance is large, we have relatively smaller decrease. And if we have small variance, GRPO can be much better than reinforced, because for reinforced, the decrease is fixed. Okay. Yeah. So this means if in the whole trajectory, the variance is lower, then GRPO will be much faster than reinforced. So consider if a question is very difficult, then the initial accuracy will be very low. The initial variance is very low, accuracy very low means the variance is also very low because it's just pi theta times 1 minus pi theta star. So the variance is low. So it means if for very difficult questions, GRPO will be much faster than reinforced in the beginning. Okay, so here is the experimental results. So first, we validate the gradient orthogonal assumptions. We can see at least in the beginning, the gradient of these different questions, they are almost orthogonal to each other. The cosine similarity is very it's nearly zero. And also we validate another assumption. We also validate the relationship between Lipschitz smoothness and the variance. We show that they are just they are positive correlated. So it means if you have a very large variance, then you have large Lipschitz smoothness. Otherwise, you have a small Lipschitz smoothness. They are correlated. Okay, so this validates our results, theoretical result, that we can use variance to capture the Lipschitz smoothness. So here is just some details about our experiments. We used the Queen model, and here are some settings. So here is the accuracy results for this data sets. So we noticed that for easy problems, usually the initial accuracy is already very high, nearly 50%. So we can imagine that for 50%, the variance is large. So GRPO does not show very good advantage compared to reinforce. But for difficult problems, in the beginning, the accuracy you can see is very low, nearly 20%. So the variance is very small. So remember that variance is small, we can use larger step sizes. So GRPO is much better than reinforce. So this means so this also coincides our theoretical findings. So this is further explanation. So we noticed that, I mean, for easy questions, we started from like accuracy 50%. And when we go to accuracy very high, like 60 or 80%, I mean, the gradient becomes very small. So even though then the variance is very small, then I mean, we can have a very small decrease after any iteration. So for easy questions, GRPO does not show like a big advantage compared to reinforce. So, but for difficult problems, I mean, we can see significant improvement of GRPO. So this also validates our theoretical findings. Okay, so here are some future directions. So today I talked about like first order algorithms for constraint problems, but still under Lipschitz smoothness conditions. So we can consider for constraint problems, suppose we want to use the local curvature, local Lipschitz smoothness assumption, can we approve the convergence rates? Also, I mean, in our proof, we make some assumptions like the gradient orthogonal assumptions. Can we relax these assumptions? Also, like in many machine learning applications, we have imbalanced data for different data samples. They might have very different Lipschitz smoothness, local curvature. So can we utilize these properties to help us design faster algorithms? So this is all about the talk today. Thank you so much.
Maybe have time for one question before we wrap up. Anyone have any questions? All right. So feel free to talk to Jiawei. Let's thank Jiawei again.